Hi there. We are looking at bonding types, ionic and covalent bonding majorly. And we should be looking at what's valency, what's the cations and anions, what's the lattice, what's the ideal and polar covalent, right? Let's look at this period, the second period, lithium, beryllium to neon. And we know the valence electrons go from 1, beryllium 2, boron 3, carbon 4, nitrogen 5, and oxygen has 6 outermost electrons, and fluorine has 7 in the outermost, and neon has 8. So the neon 8 considered as full shell, and sometimes we call the zero valency because it doesn't need anything, right? So we can just call the group number 1 to 8 as their valence electron number of electrons as well, right? So group number tells you that. Now what's specific about neon, this is full shell, it doesn't do anything, it's inert. So the below the neon, the whole family is like that. Now we look at a little bit more about the valency. Now what the lithium, beryllium, and boron will be doing, because they have 1, 2, 3 electrons, right? And we check the rest later. So the lithium, beryllium, boron will kick out this 1, 2, and 3 electrons, and they will become +1, +2, +3. They get the full shell. Look at the other side. Neon do nothing, but fluorine get 1 electron, oxygen gets 2 electrons, nitrogen gets 3 electrons. Therefore, they become anions. And the carbon is in the middle, poor carbon. It doesn't do much. That's enough for us. It no plus, no minus. But we know the beginning of the metals will make cations by losing electrons, and the end of the period will get electrons and become anions. And number of electrons will decide whether it's a -1, -2, -3, right? You can remember the plus and minus. Cation has a plus and the anion has a negative, right? Okay, so that's just a general idea. It's better to know this little Benny boy called nut orange fruit, never, and the numbers as the way I put it, right? Now, um, so also this boron to neon, up to neon, they can share electrons to make the octet or make the full shell. That's the expectation. Now we're gonna try to look at how does it work, right? Now, the easiest one to understand, look at this one, the ionic compounds. So the ionic compounds, that's a specific term, not molecules, ionic compounds. These are coming from metal cations like sodium, potassium, lithium, and non-metal anions like fluorine, oxygen, nitrogen, things like that. Now, let's get this example. Sodium has 1 electron in the valence, and the chloride has 7 electrons in the valence shell. So sodium trades the electron, gives completely to the chlorine. So sodium gets the full shell. Also, chloride gets the full shell. Now, what do we have? Sodium lost an electron, become cation, and chloride get an electron, becomes negative anion. Now they're happy because both of them have full shell, sodium plus and chloride minus. Now what happens? You can do the same thing here. Just take lithium, has 1 valence electron, and fluorine has 7 valence electrons. Now lithium can just dump the electron, trade the electron to fluorine, and lithium gets the full shell, the inner full shell, and it becomes lithium plus, and the chlorine, actually it should be fluorine, right? So the fluorine gets the full shell, right? So now we have cations and anions sitting next to each other. Okay, so these are few examples, right? So lithium, sodium chloride, and lithium fluoride, actually, right? Now what's the important thing to understand? These are not alone, these are not one atom, two atom. There's millions of gazillions of atoms, so they become plus and minus. So that's how you write them in a one-dimensional fashion. So plus minus, plus minus, plus minus, they attract each other, they sit together like a lattice. Now See, I can draw every cation is surrounded by 4 negatives and every negative is surrounded by 4 positives. That's on the screen, but just imagine on top of the screen there is one and behind the screen there is one. So it's surrounded by cations and anions. That makes the crystal lattice. And it's a solid, three-dimensional, and it has a high melting point, goes from 1000 to 2000 to, and so on. And also these are not good conductors. The ionic compounds are not good conductors. Why? The reason is these plus and minus are locked in that position. It can only vibrate a little bit. They are not going to move around to conduct heat or electricity. So that's the nature of ionic compounds, right? Now let's go to the second category. So that's a completely different one. Covalent molecules. These are molecules, specific term. The previous ones were compounds, right? Now, covalent means coexistence, and they share electrons to make the octet that really, really needed, right? To be happy, you need the octet for each and every atom and element, right? Now, let's get this example, simple one. Hydrogen, 2 atoms, bring closer. There is 1 proton, 1 electron for each. And what happens if you just share the 2 electrons together? So you can put the 2 electrons in the center, and you have 2 nucleus, which is 2 protons for the each hydrogens, right? And it should look like that, right? 2 pluses and 2 negatives. Now what happens? The negative and positive attract each other, electrostatic attraction, right? So this attraction, what happens is it's like a tug of war, or you're holding your friend's hands and pulling each other's way. That's what's happening. So 2 electrons and the 2 nucleus actually keep this thing together as H to H single bond. That's called the sigma bond. That's called the single bond. What you're doing, it's a tug of war, 2 electrons in the middle of the 2 nucleus, right? Actually, the electrons are not really staying in one location, but it's roughly 50% sort of roaming around each nucleus, right? So this kind of behavior is called the ideal covalent, because each atom shared the electrons equally, peacefully 50%. So that therefore we call ideal covalent. They are perfect sharing. So who are they? Hydrogen, fluorine, bromine, nitrogen, iodine, all these diatomic molecules do that, right? Now, the next category is the previous ones are called the nonpolar or ideal covalent, right? So I have another example later. But for this one, the polar covalent, look at this one, hydrogen and fluorine. So fluorine has 9 protons in the center nucleus, and the hydrogen has 1 proton in the center nucleus. Now, so the 2 electrons shared from each atom is in the center, right? Now, we are not really paying attention to the other lone pairs, right? But we want to pay attention to the shared these 2 electrons. Each atom gives 1 electron to the center. So those are called the bonding pair, right? So the bonding pair sitting in between the +1 and the +9. You can imagine now there's not going to be 50-50, right? That's going to be different. So the 9 plus has more pull, more electrostatic attraction. The electron cloud, because electrons are not stagnated in one place, they're just spinning around, and it's going to be more roaming into the 9 plus. And it's, if you get the snapshots, like over a few picoseconds, this is what you should be seeing. So this one can be simplified: more electron density towards the fluorine and the less electron density towards the hydrogen. This is called the dipole, or we call the dipole bond, or bond is dipole. This is indicated by delta minus and delta plus to indicate the density of the electrons, right? So the dipole, think it's like a little magnet, bar magnet. There you have a south pole and the north pole, right? This can be shown as dipole, and also the net value of it we call the dipole moment. I call it dm. It's simpler, right? So the dipole moment, actually, if it is not zero, this compound gonna be a polar molecule. So if the dipole moment is not zero, it's a polar molecule, right? Because it keeps the permanent delta plus, and then it can dissolve easily in the water, so it's a polar compound. So that's the way you want to look at. So this little picture about this polar molecule is really important to understand. So you can get similar ones, right? So look at this one, H and Cl. Chlorine has a 17 proteins in the nucleus, and hydrogen has one proton, and then the two electrons, the bonding pair electron is in the center, right? We can simplify. So now we know, same as the HF, it's going to be electron density is higher onto the chlorine, and then we can show the bond has a dipole, and it has a direction basically, and the dipole moment, the net dipole is not zero, right? It has one direction. So therefore, it's a polar molecule, right? So that's how you explain HF and HCl. So you can do more, and you can understand how do you explain a polar molecule, right? Now we're going to do a few examples to recognize whether they are uh, polar, non-polar, or covalent, or ionic, right? Let's get few examples. And there's another video actually, so I just have to finish that. So these folks have created another one, but it'll be on the way soon, right? When I have time. So let's look at these few examples. I just picked up some examples, right? So let's see how to recognize whether they are lattice, or whether they are covalent, or whether they are polar covalent or non-polar covalent, right? And not only the molecules, I put some bonds, which is HO and HN, they are bonds. Look at the calcium chloride. We know from the periodic table calcium makes 2 plus metal cation, and chloride makes minus, so therefore it should be ionic. This is not one, it's ionic, right? Look at bromine, the same kind of atoms sitting together. It's an equal sharing 50-50. It should be covalent coexistence. Again, go back to lithium and fluoride, lithium plus, fluoride minus, it's an ionic. Calcium oxide, calcium is a 2 plus, oxygen should be minus 2 because you're sitting with the metal cation. That's why it's ionic. Look at the fluorine, F2, the same kind of atom shared electrons, covalent molecule. And IBr, that's also covalent because non-metal. HO, non-metal, non-metal, covalent. HN, non-metal, non-metal, covalent, right? Now, if the bromine is non-polar because it's the same kind of atoms, right? Of course, ionic ones are plus and minus, but look at the same kind of fluorine, non-polar. IBr, different types, polar. HO, different types, polar. NO, different types, polar. Thank you.